In this video, we're going to talk about groups and periods on the periodic table, and then periodic trends and how we can predict properties simply based on an element's location on the periodic table. So a vertical column on the periodic table we call a group or a family. Horizontal rows we call periods or series, but group and period are what we will use most often. There's 18 groups and 7 periods. So that means going across the periodic table, we have a better picture on another slide. But we've got 18 groups going left to right, and we've got 7 periods going top to bottom. And we're going to talk about all the different, there's names for many of these groups, and then the periodic trends. So hydrogen is very special on the periodic table. Sometimes they'll put it, I've been drawing it in the upper left. That's not a very good drawing. But hydrogen is basically right here in the upper left. Now here they're saying we're going to place hydrogen in the middle, so on the next slide they're placing it right in the middle, but the point is it does have unique behavior. So it is a gas similar to the nonmetals, so recall that the nonmetals are over here on the periodic table, and that's where you have several gases. There's 7 naturally diatomic gases where they're gas at room temperature, and hydrogen is one of them. But it also reacts by losing 1 electron, so we're going to talk about that in the videos for this week, which is a property similar to metals. So it's a little bit like nonmetals, and it's a little bit like metals. Now, we don't normally consider hydrogen a metal, but we do place it over here on the left quite often for a very good reason, and that has to do with the way the electrons are in the atom. So on what level and sublevel they are at. So here's your hydrogen. They've placed it in the middle. Many periodic tables will have it right here, and that's fine as well. That's more common, actually. But these names here, so alkali metals, alkaline earth, noble gases, halogens, you'll want to make sure you're familiar with those names because we're going to use those names frequently to refer to these columns. Now, the lanthanide and actinide series, that's referring to these. So often you'll see periodic tables where they're split in the middle, because honestly, if we drew a periodic table with these inserted where they go, the periodic table would be an extremely long poster left to right. So this is quite often how we draw it, where the lanthanide and actinide kind of placed below the periodic table itself. But again, these groups, so this first column on the periodic table, those are called the alkali metals. The second column there is the alkaline earth metals. This column on the far right, those are called the noble gases. And this column next, where you've got FCl, bromine, iodide, etc., those are called the halogens. These others also have names, but you don't need to worry about them. For example, the oxygen group, those are called the chalcogens, but we very rarely use that name. Transition elements, so this section in green, right in the middle, those are called the transition elements. And then the inner transition elements are the lanthanides and actinides together. So again, these 4 names, alkali, alkaline earth, halogens, and noble gases. So we say 1, 2, 17, and 18 because you have basically the first, the second, and then the last 2, 17 and 18. You will want to make sure you have those memorized because those names, even outside of this course, are used quite frequently. So next, the arrangement of the periodic table means that the physical properties of the elements follow a regular pattern. So there's several different trends that we're going to look at. We can do the size, or what we also call the atomic radius. So you have your nucleus and then electrons orbiting. So basically going from the nucleus out to the farthest electron orbit or the farthest electron level, that's your atomic radius. That follows a trend. And here are the 2 basic rules for that trend. Atomic radius decreases as you go up. So in our periodic table, atomic radius decreases as you go up. So up top, they're smaller, and then they're larger down at the bottom. Atomic radius decreases as you go from left to right. So as you go from left to right, they get smaller, not larger, and there's a good reason for that. So here they've kind of got a graphical representation, so you can kind of see relative and the units that we have on here. These look like these are nanometers. I'll have to double check, but nano is 10 to the negative ninth. This is figure 5.4. Oh, I apologize. These are actually picometers. So this is on page, this table, or this figure, sorry, it's on page 139. And these values here, these are values of picometers, sorry. But the point is, you know, we can see the trend right here where they get smaller as you go up. So elements in this second row, like boron, carbon, nitrogen, oxygen, fluorine, those are very, very small. And then elements further down, like this is cesium, barium, TL, I'm forgetting now, but Pb is lead, bismuth. Anyway, these are the larger ones. And the reason for this is because as we go down, we're adding more electrons. And we talked about in the previous video, if we have our nucleus, and then here's one energy level and another energy level and a third energy level and so on and so forth, these energy levels get larger. They are further from the nucleus. And as we add more electrons to elements, so for example, cesium has more electrons than sodium, those electrons need to go somewhere essentially, and they end up going in energy levels that are further and further away from the nucleus, which is why you're going to have the larger elements further down on the periodic table and the smaller elements are up near the top. So in general, atomic radius applies to the main group elements, not transitions. So transitions, there's a little bit of exceptions. So transitions are very interesting because they can have multiple charges, and sometimes they don't follow the trends quite so perfectly, but knowing the general trend is perfectly good. Just generally that they get smaller as you go from left to right and smaller as you go from bottom to top. Now, atoms get smaller as you go from bottom to top because as you travel up a group, there are fewer energy levels. And by fewer energy levels, again, we mean fewer electrons. Atomic radius decreases as you go from left to right because the number of protons in the nucleus increases. So this is the key idea. As the number of protons increases, the nucleus pulls on the electrons and it pulls them closer, thus reducing the size. So what we're referring to here is called Coulomb's law, and roughly it's right in the formula right here. This is an approximation of the formula. There is a K constant in the front, but we really don't have to worry about that. This is starting to get a little bit into physics, but the way Coulomb's law works, and this applies to charged particles, it's very, very similar to magnets. So two magnets, like if you have the north pole of a magnet and the south pole of a magnet, or south pole of another magnet, they're going to be attracted to each other. It's very similar with negative and positive charges. They are attracted to each other. So this numerator where it says Q1, Q2, that's kind of like the positively charged nucleus with those protons, and you can think of Q2 as the negatively charged electron. Positive and negative attracts each other. R squared, R is kind of like the radius of the atom, or you can think of it as distance between the two charges that we're talking about in the numerator in the top of this fraction. And then it's squared. And then E is kind of like how tightly they're being pulled or how strong that attraction is. If you've got more protons in your nucleus, then this numerator is going to be a larger value, and then that Coulombic pull, that attraction, is going to be stronger. And then what happens when the Coulombic pull, that attraction, is stronger, it brings all of the electrons in a little bit closer. So maybe instead of being this far, they just come in just a little bit closer as you add more protons into the nucleus. And that's why it decreases as you go from left to right, because each element going from, for example, carbon has 6, and then nitrogen has 7 protons, and oxygen has 8 protons. So these are progressing left to right: carbon, nitrogen, oxygen. Oxygen has more protons than carbon. Because it has more protons, it has a stronger Coulombic attraction on its outermost electrons, making oxygen a little bit smaller than carbon. Another trend that we can look at, doesn't come up too often, but it is a trend: metallic character. So it's basically the degree of how much metallic character an element has, and it decreases from left to right and from bottom to top. So it's very, very similar to the trend for atomic radius. So we've got the two summarized together, and honestly, we're not going to look at metallic character too often, but atomic radius is very, very important for other aspects of chemistry and bonding and such. But here they've got, this is, just looking at the book, this is figure 5.5 on page 140. And they've got, just trying to figure out what exactly are they plotting with this, with the height here, and they're not saying in there. But most important thing I think to remember, to take away from this slide and this figure, is the atomic radius decreasing, and more importantly, the reason why, which we talked about on this slide, the reason why the atomic radius decreases. So as we're going from left to right, we're adding protons to the nucleus, and each additional proton in the nucleus means we're going to have a stronger Coulombic attraction between the nucleus and those outermost electrons, because positive and negative attract each other. And adding more protons to the nucleus means stronger pull. It pulls them in tighter, a little bit closer. And then atomic radius decreases going up because there are fewer electrons. There are fewer energy levels. And the 1s energy level is smaller than compared to like the 4 energy level. Another trend that's very important is called ionization energy. So we've got the word ion in here. So an ion is essentially a charged particle, and ionization energy, it's referring to the amount of energy required to remove an electron. And specifically in the gaseous state, but what we mean is maybe going from an oxygen atom that's neutral to going to an oxygen that has now lost an electron. Now recall that electrons are negative. If you remove a negative charge, that means the oxygen would now have an overall positive charge. And we'll talk a little bit more about that in, I think, the next video. So in general, ionization energy increases as you go from bottom to top, and it increases as you go from left to right. And the reasoning for this is the same as when we talked about atomic radius and Coulomb's law. So I'll write that law again. So Q1, Q2 in the numerator in the top, and then R squared in the denominator in the bottom of that fraction. So the closer the electron is to the nucleus, the more energy is required to remove an electron. So again, that R squared, that's kind of like the distance between the two charges, and in this context, you can think of it as the radius of the atom. Think about, if you have an electron that's closer to the nucleus, that means R is smaller, because the distance between the nucleus and the electron is a smaller distance. If you make a denominator smaller, then the quantity out front becomes larger. And that's why they're saying more energy is going to be required to remove an electron. When the positively charged nucleus and the negatively charged electron are closer together, this denominator is larger, and the energy required is going to be larger, or more energy is going to be required because they have a stronger pull on each other. And that stronger Coulombic attraction is what we have to overcome if we want to pull an electron out of the nucleus. Now, for the other direction, where we're talking about ionization energy increases as you go from bottom to top, that also has to do with distance. So Actually, I'm thinking we were just talking about distance for bottom to top when we're talking about this R squared. So actually we want to switch over to this one. Ionization energy increases as you go from left to right. So the reason for this has to do with our numerator. So recall, we were just saying that you can think of Q1 as the charge of the nucleus, like how many protons, how many positively charged protons are in the nucleus. And you can think of Q2 as your negatively charged electron. If you've got more positively charged protons in your nucleus, then you're going to have a stronger attraction to the electrons that are orbiting. So more protons, if we go from left to right across the periodic table, so for example, going from boron to carbon to nitrogen to oxygen to fluorine, we're adding more protons. So that Q1 quantity, you can think of that as getting larger, and if the numerator in a fraction gets larger, then the quantity you're calculating also gets larger. So as we go from left to right across the periodic table, we're adding more protons, there's going to be a stronger Coulombic attraction, and more energy is going to be required to remove an electron. Again, very, very similar theory for why atomic radius also has that trend. Same principle where we're talking about Coulomb's law. So here's an actual graphical thing on the trend, and you can see that it's kind of a spiky graph, so there's definitely some exceptions here and there, some interesting exceptions. So this is figure 5.8, and this is on page 148 of the book. So we see that the general trend is going from left to right. So for example, going from lithium to neon. So here's lithium, and going from left to right, going over neon. We see that the trend is going up, but there's a couple exceptions here, and you really do not need to worry about the exceptions themselves. But then notice that when we go from neon to the next element of the periodic table, sodium, so here's neon, and then we go over to sodium, it drops back down again. And then the trend starts to increase, and then it drops back down. And then it starts to increase, and it drops back down. So understanding the general trend is what's important. You don't need to know all of these interesting exceptions. And these, like this region, these are the transition metals. And we talked about how transition metals sometimes don't follow the trends as neatly as we'd like. So some other properties. Since the properties of elements follow regular patterns, we can predict unknown properties of elements based on those around it. So if you're talking about, let's say, sulfur right here, if you knew something about sulfur, you could predict that same property of chlorine just based on the fact that chlorine is to the right and in the same row as sulfur. That's what they're talking about with this first bullet point. So for example, table 5.2, which I was just going to find table 5.2 so I could tell you the page it's on. Table 5.2 lists several properties of the alkali metals, except for francium. And I think they've actually got it here on this one. I was just going to find the page number for you. But we can predict the properties of francium based on the other alkali metals, so let's do that. So francium is under cesium, so these are all of the elements that are in that first column in group 1, the alkali metals. So notice a couple things. So we've got atomic radius is increasing, which makes sense with the trend we already saw. So we could predict that the atomic radius for francium must be larger than 0.266. Another trend is density. It's not a trend we just talked about, but it is a trend we're noticing here. The density is also increasing, so we could predict that the density of francium must be larger than 1.87 grams per milliliter. We talked about units of density in the PSS, Prerequisite Science Skills module. Another trend, so another physical property that happens to follow a trend, melting point, is decreasing. So we could predict that the melting point of francium is something lower than 28.4 degrees Celsius. And then the atomic mass is increasing. Now, atomic mass, AMU is just one way of expressing atomic mass, but it's basically saying how many protons and how many neutrons are in that nucleus or are in that atom. And it makes sense that as you go down on the periodic table, so as you go further down, you're going to have more protons and neutrons in the atom. So remember hydrogen, we said hydrogen is element 1 and helium is element 2, and then we had 3 and 4 and then 5, 6, 7, 8, 9, etc. That's referring to how many protons are in the nucleus. So once we get down to francium, francium has 87 protons in the nucleus. Cesium, just above that, has 55 protons in the nucleus. And then rubidium, Rb, has 37, and so on. So as you add more protons, you also happen to be adding more neutrons, and that's why the atomic mass increases. We can also predict chemical properties. So members of a family also have similar chemical properties. So again, family is another name for a group or a column. So for example, all of the alkali metals have oxides with this general formula. So oxide meaning how it bonds with oxygen. So we have lithium, sodium, potassium, rubidium, cesium, and francium. All of them bond with oxygen in the same way, where there's 2 atoms of the metal and just 1 atom of the oxygen. This is one of the early ways that they organized the periodic table, by studying how the individual elements bonded with oxygen. And one trend they noticed was all of these elements bonded where it's 2 copies of the metal atom with just 1 oxygen, and that helped them group those together in one column. The formula for chloride of calcium is calcium chloride, where there's 2 of them right here. So we can predict what would be the formula for the chloride of barium. So barium is Ba, and then barium is in the second, so this is in group 2. Calcium is also in group 2. So because they're in the same group, we can predict that they will chemically behave similarly when you try to make a chloride. So you're pairing up barium plus chloride. So since calcium was 1 element of calcium and 2, not 1 element, 1 atom of calcium and 2 of chlorine, barium should behave similarly. So we have 1 atom of barium and 2 atoms of chlorine anytime barium and chlorine get together to make barium chloride. And I'm doing a little bit of nomenclature there. We will discuss nomenclature next week in another video. So next thing, new term, blocks of elements. So we kind of talked about this already. So the 1s, that was the level that was closest to the nucleus. And then the 2s came after that, and then we have the 3s. Now, in terms of this order, we'll get to that when we talk about electron configurations, but the important idea for right now is that 1 came first, 2 was the next closest, and then 3 was the next closest, and then after 4. But we can break the periodic table into blocks of elements where it's telling us how the electrons are going into those levels and sublevels. Now, just a quick note on this notation. So we've got 1A/1 and 2A/2. There's different, just finding the page number, because it's kind of interesting historically. So on page 138, they talk about all of the different group numbers, different ways that we will label the columns on the periodic table. And I personally just like the, group 1, group 2, group 17, group 18. But the point is that there's been other ways of labeling those columns over the years. So that's why you're seeing this interesting numbering system. But another reason why we might want to stick to the name. So instead of just saying group 1 or group 1A, we'll just call it alkali. But regardless, those first 2 groups, so this one, this is just the first 2 columns, they're filling the S. So when those elements need to find a home for their electrons, they end up putting them in S. And it's more specifically the outermost electrons they're putting in the S. And then next one, so this grouping, it says 3B/3. So basically 3 through 12, those are the transition metals. So that big chunk in the middle of the periodic table, that's what we call the D block, because when they are taking their outermost electrons and finding a home for them, they're putting them in D sublevels. So those are those flower-shaped orbitals that we talked about in the previous video. Inner transitions, so that section of the periodic table that's below the periodic table itself. So the inner transitions, those are putting their outermost electrons in F, and it's not on here, but then on the far right, you have where the nonmetals are. So this section of the periodic table, that's where you have where you're basically putting your electrons in the P. But we've got it summarized much better here with a much prettier picture than my scribbles. But we can use the periodic table to predict which sublevel is being filled by a particular element. So starting with hydrogen, hydrogen has one electron, and that one electron has to go somewhere. So it goes in the first level and on the S sublevel. So that's why it says 1s. Next over here, this is helium. Helium, one more proton and one more electron in that atom. That electron needs to go somewhere. And we recall we said that the S sublevel can hold 2 electrons. So that second electron is also going into the 1s. Next, when we get to lithium, so lithium's right here. Lithium is element number 3. It has 3 protons and 3 electrons. Those first 2 electrons are still in the 1s, but that third electron needs to go somewhere. The first level is full, so next we go into the second level, and it happens to go into the 2s. And we'll see this trend where every single time we get to an element that's in this pink colored, it says it's calling it S block elements, we end up putting that next electron in an S sublevel or an S orbital. So in green, we've got what we call a P block, meaning, once we get to, this is beryllium, and then here's boron right here. Once we get to boron, boron is element number 5. It has 5 protons in its nucleus, and it has 5 electrons orbiting the nucleus. The first 4 electrons have homes in the 1s and 2s sublevels, but then that 5th electron needs to go someplace. It goes into the 2p sublevel. Next example, let's pick out fluorine. So this is where fluorine is. Fluorine is F. Fluorine is element number 9. It has 9 protons in the nucleus and 9 electrons. Those first 4 electrons have homes in the 1s and 2s, but then the remaining 5 electrons need to go someplace, so that, again, they go in the 2p. And since fluorine is kind of 5 elements in, going from left to right, it has 5 electrons in that 2p. And notice that this section of the periodic table is 6 elements wide. We said that P sublevels can hold 6 electrons. Another thing to notice, the D block. So this section in orange, this section of the periodic table, if you count, this is 10 elements wide. And this is the D block. And we said that D orbitals, so all 5 of those collectively together, can hold 10 electrons. It's 10 elements wide. It can hold 10 electrons. And then F, if you recall, we said 14 electrons. This happens to be 14 elements wide. So when we get to electron configurations, which is another video, but it is this week, we are going to be relying on this trend in the way the periodic table has been organized, because this can help us figure out where the electrons are and write out the electron configuration for any element simply based on its position in the periodic table. So no memorization required. You can figure it out each time. So I think I said the term valence. I may have thrown that word around, so let's actually define it. So valence electrons refers to outermost electrons, and valence electrons are interesting because those are the electrons that participate in chemical reactions. So when an atom undergoes a chemical reaction, only those outermost valence electrons are involved. So these electrons are of the highest energy, so meaning they're furthest away from the nucleus, and they are called the valence electrons. Valence electrons are the ones that participate in chemical bonding. So the valence electrons are pretty much just the S&P electrons beyond the core electrons. So what we mean by core, so if here's our nucleus, and here's level 1, level 2, level 3, level 4, and let's say, for example, let's do calcium as an example. So calcium is element 20. This is number 20, so that means there's 20 protons in the nucleus. It's going to have 2 electrons here in that first, so this is number 1, 2, 3, and 4. Number 2, level 2, it's going to have a total of 8 electrons. And calcium is on the 4th row of the periodic table. So if you have a periodic table handy, you can take a look at it. You'll notice that calcium, element number 20, is on the 4th row. So those first 3 levels are going to be totally full. And level 3, it can fit a total of 18. However, and when we get to electron configuration, it'll make a little bit more sense, but it also happens to have 8. And 8, 16, 17, 18, we've got 18 electrons accounted for. That means there's only 2 electrons left over in level 4. We are saying that these electrons here are the core electrons, and these electrons out here on level 4, those are the valence electrons. And it's these 2 valence electrons that participate in chemical reactions. So valence electrons are the electrons that are furthest away from the nucleus on that outermost energy level. And the core electrons are everything that's closer to the nucleus. Core electrons do not participate in chemical reactions. Now they're calling it the noble gas core because remember, this column here, these are basically the noble gases. One thing that's very special about the noble gases is their energy levels are completely full. And because they're completely full, they essentially do not participate in chemical reactions at all, which is one reason why you can breathe helium in from a helium balloon and it comes right back out through your windpipe, making your voice sound funny, and you will have no ill effects because the helium does not react with your body. It just makes your voice sound funny, which is very entertaining, but not harmful to your health, other than the fact that you're not breathing oxygen when you do that, you're breathing helium. But it doesn't have a chemical reaction with your body, which is why we can do that. Now, we can predict how many valence electrons an element will have simply based on its location in the periodic table. And again, here's that nomenclature that I don't particularly like, but group 1A is basically that first group of alkali metals. And then 5A, so 5A is basically the 5th column going from left to right. They have 5. So V is your Roman numeral for 5. I prefer just the regular one. So like this is group 2. They have 2 valence. Now group 14 is way out here. Let me draw a little periodic table schematic. So group 14 is like right around here. They have 4 valence. So that's 2 from the S section and then 2 more from the P section. That's how they got up to 4. But the point is that the location of an element in the periodic table can tell you how many valence electrons there are. So let's go back to this periodic table, even though it doesn't have the elements on there. So for example, this element here, because it's in the 2nd column going from left to right, we know that there's going to be 2 valence electrons. And then here's another example. So this element, this location of the periodic table, without knowing what the element is, we're going to have 1, 2, 3, 4, 5 valence. So all of the elements in this column will have 5 valence. And then this column, so if you remember that this column here, these are the halogens, they will have 7 valence electrons. So simply based on its position in the periodic table, we can predict how many valence electrons an atom will have, and thus how it, or what kind of ion it forms, which is what we're going to talk about in the next video, and how it participates in chemical bonding.